So now I want to talk about functions. So we kind of hinted around it a little bit, but today we're going to actually dive in. So functions are sort of the start of how you start to really organize your code, right? They're kind of the fundamental tool in breaking your code up into useful pieces and reusable pieces. And that's a huge part of how you actually become an engineer. You have to start thinking in terms of breaking things down into smaller parts and keeping things really compact. Those same ideas will later feed into things like object-oriented programming and go to calculation, but it all starts with functions, right? The first wave. So let's talk about functions. So we've seen one function a lot, right? So we've had this one int main we've used for everything. We have to have, and that's kind of a special case, the main function, because that's just by convention in C++, you have to have a main. That's how the computer knows where to start. You'll see similar things in other languages sometimes. Sometimes it's more open. But anyway, so let's kind of dive into this a little bit. So every function has a signature. One way of talking about its key components. So every single function, not just in C++, but in any language ever, right, conceptually has a few key parts. It has a return type. We'll talk more about it in a minute. So it's output, right? Because again, a function is kind of like a black box. Right? We talked a little bit about the concept of a black box, and then it's a box you can't see into. All you can see is the outputs and the inputs. Kind of like, think of it like a VCR, right? You got, power goes in, and VCR is a horrible example, but all of that stuff is outdated, right? I don't know, your Wi-Fi router, I guess. There we go. So power goes in, right, and internet comes out, right? And they're often black boxes. So maybe that's one example. But the key thing is, you don't really have to know what goes on inside. You do have to understand what goes in and what comes out, right? If you try to plug in your Wi-Fi router to a 9-volt battery, it's not going to do much for you, right? You have to plug it into 120 volts AC wall power, right? Like every other appliance. So, right. So we've got an output type or a return type. Might be empty. We've got a function name, which is always something, right? So main. And then we have 0 or more inputs or arguments to the function. Now, every function might have no output and it might have no input, but that's what makes up a function, right? The signature is the return type, the name, and however many inputs it has. So, if we want to make a simple function to add two numbers, let's say, so we might do this. Okay, now so far this isn't quite going to work, because so in C++, right, we start out, the first thing about a function is always the return type. So when you say, int in this case, we're basically making a promise to the compiler. At the end of it, we're going to spit out an int. We might do various things to get there, but we're going to spit out an int, right? Kind of like, if you have an assistant, let's say, you ask them to go get coffee for you. They might go to various different coffee shops, right? There's probably at least half a dozen Starbucks within a couple blocks from here, right? So you don't know what Starbucks they're going to go to. But if you ask for a latte, assumably they're going to come back from that process with a latte, right? So it's kind of like, that's, latte, please go get latte. Oh my God. Anyway, but it's a promise, right? So if we say int, we're honor bound to spit out an integer, one way or another. Okay, so then we have a name, right? So the name of the function obeys the same rules as name of variables, right? So letters and numbers shouldn't start with a number, can't have underscores. Generally, you'll see camel case. This is the most typical thing, right? So generally, that's what you see. But let's say that. Let's say about that. And then we have arguments, maybe, right? So sometimes functions will have input, sometimes they won't. Sometimes they'll have output, sometimes they won't, right? So in this case, we're adding two numbers. So, conceptually, we have to put in two numbers, and we get out a number. right? So what we see here looks a lot like declaring a variable, and we kind of are in a way. So what we're really doing is we're saying this is the type and number of variables that are going to come in, or data that's going to come in, right? So in this case, we're going to have an int, which we're going to refer to as a. So be very careful about how we talk about that, right? It's not. It looks like we're declaring something, but we're not really, right? We're going to feed in an integer, and we're basically going to temporarily label it a. And we're going to feed in another integer, and we're going to temporarily label it b. So the way we use this, I know I haven't written it yet, but we're going to later on we can call it by saying int result equals add 2 comma 3. Right? So, oh, and I should mention parentheses are also part of the function. It's part of the syntax of saying what the argument is. That's nearly universal, but not every language does that. There's always this concept of maybe a return type, maybe some input, and a name. And this is the most typical way you'll see it, but other languages are different. Okay, so what happens is we say add to, right? So we invoke a function by having the name and parentheses. Sometimes, especially in other languages, you'll see just the name, because some of the languages, JavaScript is a notable example. It happens a lot of other places where you can treat a function as a variable. You can do that in C++, it's a little more involved. You have pointers to functions. Don't worry about that for now. But when you see the parentheses, we're invoking the function. Right? So function name, parentheses, we're invoking it. Meaning, please go do it. Right? So what happens is the computer, right, we're starting at the top of our code, we start at main, right? We hit add 2, that was defined up here, so we jump to add 2. So it's kind of like Inception, right? So you go another layer in, just realize it creates that movie. Good metaphor. So you go one layer deeper. You guys see Inception? Okay, yeah. So think of it kind of like that. So we go one layer in, right? When we go from this function to this function. And then at some point we jump back out. Right? So that's what our return statement does. It jumps back out one layer out. Right? And we can carry stuff with us. So, in Inception, they were going into that guy's head to try to get some information, right? So they can come back with that information. Yeah, Charlie. Good question. Ready? I'm going to come back to that in a minute. So, very good question, though. So we are doing that for now, right? And I'll show you what happens if we don't do that in a second. So, we pass 2 and 3 in. So we get int a and int b, which is equivalent to saying, and not that this would actually work, this is what I'm about to show you isn't proper syntax, but it's like we're saying int a equals whatever the first thing passed in was. Right? So a is, we might have had so in this case I'm passing in literals, right? So I just have 2 and 3, right? I could have another variable. I could pass in a variable, an int variable. Right? I could do this. I could say, I'll move this declaration up here. And I'll pass in my_num, right? Now, within this function is my_num defined. If I say, cout, for example, my_num, is that going to work? No, right? It's not going to work because my_num is defined in this scope, right? It's defined in main. Now we pass it to add because it's a simple integer. We're doing something called pass by value. So when you pass things around from function to function, there's 2 ways you can do it. You can either pass the actual value, or you can pass by reference. So it's kind of like let me give a good metaphor for this. It's like you can either say, here's a 2, or you can say, please refer to the number stored at this location. So you don't generally do that with an int. simple types like integer are just passed by value. I mean, we're essentially almost taking a copy of it. Right? So pass by reference is a little more involved, and we'll see it again. Again, we're edging towards pointers. Right? We'll eventually get the pointers. You guys will be fine. I'm scary, but I have faith. It'll be awesome. It'll be all right. But I do want to kind of, sneak them into almost every class, so it's less scary when we get there. So a pointer is just a location in memory. Like I showed at the start of class, right? The XKCD comic, the guy saying, I'm having trouble with this game, can you give me some pointers? And his friend just spits out some hexadecimal values, right? So addresses in memory. So for things that aren't simple types, like ints and floats, right? Things get passed by reference. So we don't actually say, here's a copy of it. We say, here's where it's stored. Reference that. So that has repercussions for if we change it inside of it, right? So if, in this case, if I said A equals A plus 1, so my num gets passed to add 2, right? So A, in this case, A starts out equal to 23, and B is equal to 3, right? Because we got my num, which is 23, and then we pass 3, which is B, right? So at this point, what's A's value? 24, right? That has no bearing, though, on my num. So once we jump back out of this function, my num is unchanged, because we pass by value. If we pass by reference, that wouldn't be the case. So if we're making a copy of a thing and then we edit it, right? Doesn't change the original. If we, reference it by its memory address, and we make changes, it does change the original. So there's some subtleties there, which we're not dealing with quite yet, but will come up later, and I want to get you guys ready. So these are local variables. Right? They're local to this function. They start out, at least in the case of integers and other simple types, they start out with a copy of the value, and then we can do whatever we want to them without changing stuff outside. Yeah. Right, because the global. Right. Good point. Right. So, well, actually, okay. Good question. So maybe, right, it would be a little unclear. So what you wouldn't want to do ever is this. You wouldn't want to say like int A global, right? And then have an A here, because now what are we referring to is A. It's ambiguous. Right, so never do that. Global variables have their place, but make sure that you don't reuse names. Yeah. Okay, so this is pretty simple, right? We want to return just A plus B, right? So again, so with an int, we said int, right? So we're promising the compiler that we will return an int in all cases. The in all cases is important. So a really easy thing, and I've got this on the handout and the class material, but a really easy thing to do, an easy mistake that a lot of people make when they're starting out, is they'll have a pathway through a function that doesn't return anything. Which is okay if the function doesn't have a return type. Right? So let's say we had a function that didn't need to spit anything out. In C++, what we need to do for that is we need to use the void keyword. So void my function, like let's say greeting. Okay, so here's an example of a function that takes no input and has no output. I mean, it does something, right? I mean, there's a cout, but there's no return value. So that's where you have the void keyword. So C++ insists, it mandates that we always specify a return type even if nothing gets returned. So other languages just let you not say anything sometimes, right? C++, we still have to say if nothing comes out of this function by using void. Then we have, the rest of our right? So that's fine, and that's totally cool, right? Some functions don't have output, that's okay. Some don't have input, that's okay too. But if you have a return type that's not void, you must return in all cases. So what can easily happen is something like this. So let's say we wanted to do, let's say we wanted to be a little safe here, right? So, making a function to add two numbers like this isn't really all that useful, right? What might be useful though is let's say we want to add two numbers and make sure that the result is positive. So you want to say if, somehow we get two negative numbers in, we return 0. Because we want to make sure that there's no possible way for the output to ever be negative, right? And so we'll do stuff like this all the time when we get into object-oriented programming. So you'll have, what a typical thing to do is you'll have a variable tied to a class. So, what's a class? We'll talk about that later. But conceptually, it's like, you define what a monster is, let's say, in terms of the game, right? I keep going to ogres, right? So let's say we got ogres in our game, right? So that ogre might have a health point, right? Or 8 hit points. It doesn't make sense for hit points to ever be negative. Probably, right? You're either, you have some number of positive points or you have 0 and that monster is dead. So you want to make sure that things never go negative. And, so you want to build in checks. So let's say we wanted to make sure that if this is negative, we only actually add the two numbers and return them if the result's positive. So here's one way we can do that. If A plus B greater than 0, let's say greater than or equal to 0. Okay, so that would kind of do it, right? But what happens if it's less than 0? Do we return anything that's written there? It doesn't, though. Right, that's what we should do, right? But it doesn't do that yet. So, you're right, that's what we want to do, right? But I wanted to kind of show you guys this, because this is a really easy mistake to make. So, this is a good way to get into problems, right? So, we've got some conditional here, right? So, we've set up a function that has an int return type, meaning that we must always return an int no matter what. Inside that function, we've got a condition. If looking like some. So we've got if a plus b is greater than or equal to 0, right? Which is totally fine too. And we've got a return value there. That's fine. But what we need to also do is we need to make sure that if that fails, if we don't hit this return, we need to make sure that something gets returned. Okay? So here's another thing we could do. It would also not be quite as good. Yeah, not type today. So this is better, but still not what I would recommend. Right, so we've got if, then we've got an else, and we're going to return 0, right? So sure, this is a really simple example, and one of those two is guaranteed to hit, right? There's no way that in a simple if statement like that, we've got an if and an else, right? One of these two is guaranteed to happen. But you should be more paranoid than that. Yeah. Being a good programmer or an engineer is a lot of the times it's about cultivating a certain kind of healthy paranoia, right? So we want to make absolutely positively certain that something gets returned no matter what. So this is not how I would do it. What I would do is I would just say this. And that might look weird, right? But the key thing to know is that return will always stop the function. So if you hit return, we jump back out. So it's like, in the layers of Inception, we go up a layer, right? And whatever was going on and where we were is just disappeared, right? So anytime you hit return, nothing else in that function happens. We go back, in this case, to main. As soon as we hit return. So sometimes you can have multiple return statements. It's somewhat a matter of style. You know, another way to do it is we could do this. We could say, and this is actually probably how I would do it in this case, this specific case, is I would say something like this. I'd say int result equals a plus b, and then, you know, if result less than 0, result equals 0, return result. It'd be a different way to do it, right? Some people, you know, I've had programmer friends that really hate multiple return statements and a single function. I personally don't feel that way about it, but the key thing, though, is you have to make absolutely certain that there is no way to navigate through that function and not hit a return statement if you have a return type. This is a little bit nicer in this specific case because we're only doing the addition once. So that's the kind of thing you want to think about too, right? So here, this is a little inelegant. The second, this is a little inelegant because I've got a plus b happening twice. Now, granted, that's just a single addition. It's not a big deal, but you want to think about that kind of thing, right? Like every cycle is precious. You want to use it. Okay. So that's pretty much it, right? So you can have any return type with built-in types. You can have arbitrary. So, and we're going to talk more about this when we get to pointers. I know I say that every class, but pointers are what make people run screaming, right? So it's good to kind of touch on a little bit every class. So once we get to pointers, you generally don't, like, let's say we do, I'll go back to my buddy the ogre, right? So let's say we're making a game and we've got an ogre class. Generally, you don't usually actually return an ogre. When you have a more complex type of data, you return a pointer to the ogre. So you don't say, here's the ogre, like we do with an int, right? We say, you know, here's the address where everything that represents that ogre lives in memory. So, yeah, don't worry about that too much right now. But yeah, so return type might be void, function name, and then some number of arguments. Another thing we'll see more of when we get to object-oriented programming is you can have the same function name repeated with different arguments. So that's called operator overloading. Well, not necessarily operator, but function overloading, and can be a really useful thing. So in C++, there's no way to have a single function respond to ints or floats, right? Like we can write a function that responds to ints, takes 2 ints. We can also write a function that takes 2 floats, right? We can name them the same though, so it ends up kind of feeling like we've got one function that does both things. Because adding 2 ints is slightly different than adding 2 floats. So something we can do. I'll talk about it more. Okay. So I want to get to Carly's question, which is really good. What do you always have to put your functions above main? So no is a simple answer, but let's see what happens if we put it below, right? So I'm going to prove that this works, right? So I'm going to let's add result. Right, so we see 26, right? We've got 23 plus 3, exactly what we'd expect. And we see some other stuff from other things we talked about today. All right, so what I'm going to do is I'm going to take this whole function and put it below main. And it's not going to work. So let's go ahead and try that and see what happens. So we get error. We see add to identifier not found. So this is a really good example of how computers are dense, right? So this file absolutely defines add to, right? You guys saw what I did. I just moved it below main, right? Same code that just ran fine. However, what's going on is we make use of it before we define it. So this is a fairly significant way that C++ is different than a lot of other languages out there. You guys might have used JavaScript, I know some of you have, and it doesn't really matter. And JavaScript and a lot of other languages. Generally, languages that are a little higher level, like more abstract, right? They're doing more for you. They're putting more layers between you and the machine. So that's the kind of nicety you get with more levels of abstraction is, the order in which you define functions doesn't matter so much. Not the case with C. Right? It does matter because C++ is not really that. It's a high-level language, but it's a lot closer to the metal than a lot of languages you might encounter nowadays. Right? So, so we got a problem. Right? So I'm just going to go with this for a little bit. Let's say that, so obviously one easy solution here is we can just move our add2 function above main. That's fine. Right? When the compiler chews through it, it finds add2, compiles that, and then when we hit it in main, it's fine, right? So that totally works. But let's say we have some reason to have add2 down there. There is a way we can get around that with something called forward declaration. So what we're going to do is we're going to just have a stub where we're going to inform the compiler. We're going to say, hey, there's going to be a function named add2. It's going to return an integer, and it's going to take 2 integers as input. And I promise you I'll define it later. But just so you know, it's coming up. I'll get to it later, but you know it's going to look up. So right now it doesn't work, right? Because we make use of something we haven't defined. So if I say int add2, int a, int b, semicolon. So what I've just done is I haven't implemented it, right? I haven't defined what it does. If I just did this, I get an error too, right? Because I have to actually implement the function. I'm going to make use of it. But that gives the compiler what it needs to make it work. So why would you do that? Well, honestly, there's not a good reason to do this specific. If I was doing this, I would just put everything above main, and that would be it for a single first line. But the reason I wanted to show you guys this is because it goes to something we're going to see later. Right? So eventually, when we get into object-oriented programming, there's going to be such a thing as a header file, which is kind of like, it's conceptually pretty similar to what we're doing here. So what we're saying is, there's going to be this thing add2. It exists. It takes 2 integers and produces an integer. And we'll get into the details of it later. Right? That's what we're telling the compiler. And we make good on that promise later, right? But we give it this little bit of information, kind of hinting at what we're going to do later. Then we make use of it and eventually define it, right? And eventually what we're going to see is that's something that comes up again later. So, just to be clear, I'm not saying you should actually do this with your functions now. I mean, do it if you want to try it, but this concept of we're going to have just a definition of the skeleton, the inputs and outputs of a thing, and then later, in some other way, we're going to define what that thing actually is. It's something we'll see again later in this semester. And I just wanted you guys to know about it because, when you have a bunch of functions, right, that are calling each other, it's really easy for them to get out of order in some way. And, if you've got things that are referring to each other, you might actually need to do that. But in practice, at least for now, I recommend just keep your main function at the very bottom of your file. And questions? Yeah. Great question. So, you can't, at least in C++, you can't return multiple types. So what you can do is you can return something that contains multiple pieces, right? But, so you have to kind of structure, this is one of the things that you do. So, with object-oriented programming, right? So you define, And so again, let's go to the ogre, right? So we've got an ogre that has a lot of information about him. Name, health, inventory, whatever, right? And so you might return that whole thing, right? And you are returning multiple things, right? There's a bunch of information that goes into that ogre, but you're not returning multiple pieces. You're kind of grouping them all together in a single box and returning that one box. So a lot of times you'll want to do that. The right way to do it is you wrap it up in an object. Or a struct is another way to do it, but that's kind of a speed thing. If you encounter structs, I mentioned it, so I'll just lose that thought. Struct is kind of a proto-object-oriented thing you might see if you look at the C stuff. And so a class, a real class, object-oriented class, right, or object. What makes it a class and what makes it an object, what makes object-oriented programming so cool, is it links data with functions. You have wrapped up in this nice, neat little bundle data, like the hit points of the ogre, and functions, like ogre.attack, or run, or whatever, right? A struct is kind of something in C that only has data. So, yeah. So you also said you can operate on more than, I wasn't sure what you meant by that. So. Sure, yeah. Okay.
So is there a way to both of those?
Well, sure. Oh, so you can have as many inputs as you want.
I mean, I wanted to see that.
Okay. Yeah. So you'd want some way of maintaining that, right? So one way to do it is an easy way to do it for now is have global variables, right? Which is totally fine for now, right? Later on, what you'd want to do is have something, you pass in a reference to some sort of state manager, right? You might, you might have something that has a link. So you might have a weather manager. A lot of times, what you'll do is sort of in place of global variables, what you end up with is there's this concept of a singleton, meaning a class that there's only ever one of, which gives you the benefits of object-oriented programming. Things are nicely encapsulated, but it still gives you one thing, right? Like it doesn't make sense to have more than one weather in your world, right? There's just weather, right? One, right? But you still want everything that deals with weather to be in one nice place, right? So you don't have code for weather spread out all over, right? So you might have a weather manager, and then you might pass in a reference to that, so that your function is doing stuff to weather and luck. It might have a reference to the player to say, okay, you are now unlucky, and the weather is now raining. And those could be totally different things, right? You could have, a whole bunch of player characters and just one weather manager. So that would be, sort of be, again, we'll talk about how references work later, but instead of like int and int, it would be reference to a player character and reference to the single weather manager. And you can modify stuff inside it. You might not even return anything in that case. No, that's a lot of stuff. That's a lot of. Yeah, for now, just use global variables. It's totally fine, right? It's okay. We'll get all this up later. Okay. All right. So we'll wrap up today with an example of something called recursion. So you can't get through an intro programming class without talking about recursion a little bit. Not because it's a good thing to do, but because it's interesting, and it helps kind of get you in the right mindset of how you want to attack problems. So there's things you have to kind of, it's a good sort of toy way of getting at algorithms and data structures better. So I'll talk about it. So we're gonna do the classic example of recursion, and then we're gonna calculate a Fibonacci number. So figure this out. And I'd like you guys to follow me. So first off, what's a Fibonacci number? So Fibonacci sequence is just a sequence of numbers. It's kind of cool. It's got a lot of, it does show up in nature in kind of cool ways. So it turns out that if you look at plants tend to have spirals, and they always basically have Fibonacci numbers in spirals. So if you look at like a sunflower, there's a number that's kind of like, I'm not explaining this well, sorry guys, but you can count the seeds kind of spiraling out clockwise and spiraling counterclockwise. And the numbers in that, in sunflowers and other plants, are always members of the Fibonacci sequence. So what's the Fibonacci sequence? Well, it starts, by convention, the first two numbers are 1 and 1, or 0 and 1. And then the way you get the next number in the sequence, so we start with 1 and 1. And then the next number is these two numbers added together. So the third number is 2. What's the fourth number? 3. 8. 13. And then it goes on and on and on, right? So let's label these with, index, right? So let's say this is the 0th number. This is the first number, the second number, third number, fourth, fifth, sixth, etc., 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 right? So let's say that we want a function that will give us the in Fibonacci number, right? So if we give it 1, we should get 1. But if we give it 5, we should get 8. If we give it 6, we should get 13. If we give it more than that, we should get more than that, okay? So what's tricky about this is we've got this sequence, which is really simple, right? Like, you can describe it very quickly, right? It's easy to do. Pencil and paper, pen and paper, it's easy to continue that out, right? But any given number is defined in terms of the two previous numbers. So this ends up being a really good example of when recursion can maybe be a good thing. So what's recursion? Recursion means having a function that calls itself. So it can be a good way to break down otherwise tricky problems. It can also be the cause of tricky problems. Right? So what recursion does, or rather, situations where it might be a good idea to use recursion is when you've got a problem that can be broken down stepwise, right? So if we want to define the 6th number in the sequence, right? Well, it's easy to say, well, that's just the 5th plus the 4th. And then that kind of begs the question of, well, what's the 5th? Well, that's the 4th plus the 3rd. And then that begs the question of what's the 4th, right? So and it goes on and on and on, right? Until we get down to 0 or 1, which we just define as 1. So for recursion to work, you need something that's a base case, right? It has to be a problem that can bottom out. And there has to be some end to it, right? So you might start all the way over here, right? You might be asking for the 100th number in the sequence. But if we go all the way over here, eventually we hit these two, which are just defined as 1. Right? So if I ask you to write a function that would give me the Fibonacci number, but I promise you that I'm only ever going to ask for one of the first two, what does that function look like? Now it's going to return an int, right? Named after an Italian mathematician. Probably. So I'm going to say int n, right? Now, let's say that I'm only ever going to ask for these two. Like, forget about that, right? What is that function? What do I want to return? 1, right? Pretty easy. Yeah, that's easy, right? That's our base case. Now, that's not going to give us everything, right? It works for the first two inputs and none others. Okay? So what I'm going to say is if n equals 0 or n equals 1, I'll return 1. Now here's where it gets interesting. So otherwise, right? So if we're here, I know I'm asking for at least the third number in the sequence. Right? So how do we define the third number in the sequence? It's this plus that, right? So it's the third number is the second number plus the first number, right? So for any Fibonacci number, fib n equals fib n minus 1 plus fib n minus 2. Right? Now, if we don't have some sort of base case, though, this is going to go on forever, which we don't want. Right? So that's why it's important to have this base case. So if we get down to 0 or 1, we just spit out 1. If we have at least the third, though, we can do that. So what we're going to say is return that's it. That totally works. Up to a point. So I said up to a point. What do you think you're wrong with? Yeah, I did. Oh, good thought, right? Yeah. Good point. So a non-negative integer, it will never go negative. But you're right. We could check to make sure that it's so I'll rewrite this logic a little bit to fix that. Good point. What we'll say is if n less than 2. Right, so now we got, it definitely includes 0 and 1, but if we somehow put a negative 1 in there, it would just return 1. Okay, so that's a good point. But, so there's another way that this could go wrong, though, and I'll give you a hint. Conceptually, it's fine. So the logic of this is totally fine. This is a totally valid way to define Fibonacci numbers of any point in the sequence. You can have the million to the millionth power Fibonacci number. And this conceptually would be fine. But it would not run at all.
How we can do about other order, I mean 3, 4, 3, and 4, because we define n only under 2.
Right, so this is just by definition what the Fibonacci sequence is, right? So it's used as an example of something that benefits from recursion, but it's just by definition the first two are 1. That's why we lock it at 1 for anything under 2. So the third is when it starts getting self-referential. So the key thing to point out about this, though, right? So this is where recursion gets really, really dangerous. So let's say we call. So let's just do this, right? So I'll run it, and let's go for the 6th number on the sequence. And we should see 13. And we do. We see 13, right? So cool. Awesome. Well, so that works. So we can probably crank it up, right? Let's go at 600. Well, let's try, 100. Nothing showed up. Yet. Why do you think that is? We didn't get an error. What's going on? Number 6, well, you're close, right? It's way too big. But what's going on is that we're outstripping our memory. So every time we call a function, right, we maintain a reference. So we're going down a layer, down a layer, down a layer, down a layer, right? So if we call Fibonacci 6, right, it spawns, so Fib 6 spawns Fib 5 and Fib 4, right? Fib 5 spawns Fib 4 and Fib 3. This spawns Fib 3, Fib 2. And it keeps on going, right? So this spawns, etc., etc. I actually just write it all out. So here, that's an end. All right, so we get down to 1, so that gives us an end. Okay, so that's one expansion. All right, so I won't draw the rest of it, but the point is that as we keep calling new functions, right, recursive functions are really dangerous because notice it's still going, right? Because what's going on is we have to expand all of that before we hit the bottom, which is not the case where we just call a normal function call just does what it does and returns, right? The dangerous thing about recursive functions is they keep adding to the stack. So this doesn't actually finish until we've expanded all the way out to here, hit our base case, which just spits out 1, right? And then we go all the way back up before this function ends. So even though 100 isn't really that big of a number, right? And you know, any of us could sit down and actually get to the 100th Fibonacci number in probably not that much time, right? Maybe an hour at the most, right? Doing it out by hand wouldn't take that long. But even though this, we're running on a nice modern 26, getting the 100th Fibonacci number is still outstripping all available resources.
So it's 1 now?
Yeah. So yeah. We're going to have to actually kill that. So why are we even talking about recursion? Right? So recursion can be a good way to attack some problem sometimes. Honestly, you probably don't want to do it. If you're thinking about using a recursive approach, be very, very careful. Think about it long and hard. Make sure that the inputs are pretty small. But the real reason to talk about recursion, at least in my opinion, is it's a good way to start thinking about how does the number of steps the computer performs change as the number of the scale of inputs changes. Right? So there's this thing that you guys will learn about more as you go on in your career learning about programming. There's something called big O notation. Right? So it's a way of analyzing what a computer does. So let's say we've got a problem and we come up with some approach, some algorithm to solve it, right? We have it's really important to know, is that a reasonable way to approach that problem? How do you know, right? It's really easy, almost anything. I mean, computers are so good now, right? They're so fast, they have so much memory, that with a small amount of input, you can do pretty much anything, right? You don't even have to worry that much. You can just brute force everything, right? You've got a small amount of input. But as that input grows, how does the number of steps change, right? So what we're seeing here is a geometric expansion, right? So if I ask you to add numbers, right? Adding 2 numbers is 1 operation, right? Adding 3 numbers is how many operations? Right? So we have A plus B, that's 1, right? A plus B plus C is how many? 2, right? And as we keep adding more numbers, the number of operations just goes up by 1 each number, right? It's something called a linear progression. So if we have 10 numbers that we're adding, and then we go to 20, it'll just double the time, right? That's okay. That's really not that bad, right? So as your input goes up, you have linear number of steps, right? Straight multiple. Now let's say I've got I've got a collection of things, and I want to compare everything in that collection to everything else in that collection. Right? So I've got, 5 things, and I want every possible combination, I want to test them in some way. That's not linear, right? So if I've got 5 things, I have to compare each thing to the 4 others, right? So I end up with 5 times 4. I get 20 things, right? Which is totally fine, not a big deal. But as the number of inputs increases, it's not linear anymore. It's much bigger than that. So that's one of the reasons, at least I think that's really the best reason to talk about first getting started, is because it's a really good early example of how things can blow up on you. So this is a reasonable way to approach getting the Fibonacci number for a small input. Okay? But one of the things you guys want to cultivate as you learn more about programming is sort of a sensibility about how things grow as the input grows. Because a lot of the times, almost anything will work if you've got small inputs. But in a real world situation, you can easily get, even though modern computers are really fast and have tons of memory, once you get geometric growth going, you can quickly get to something that would literally take longer than the universe has existed to execute, right? So, and that's how you start to get into what a good implementation versus a bad implementation is. And that's where you get into the really, really fun stuff about computer science, where you take stuff that a sort of naive approach, right, would require an n squared or a really geometric progression, and you come up with a clever way to reduce it to linear or less. So that's where it's a good example of how it can get really bad. And you want to be really careful, because if you have an approach like this, right, I guarantee you'll test it and it'll be fine. Okay? Because you'll test it, because it's really hard to get yourself to be mean to yourself. And it's hard, there's something else you want to cultivate, is actively trying to break your own code. You don't really want to do it. You'll kind of subconsciously give yourself nice inputs that are reasonable, right? But then you put your code out in the wild, and there's not just one enemy on the screen. There's 100, or maybe just 10. 10 can be enough if it's something like this, right? And I put in 100, which is not a big number, right? And we didn't get our output because our implementation had geometric growth. So like that. And know that there's incredibly cool stuff that very brilliant humans have done to take things that would normally be geometric and reduce them to less than that. Sometimes drastically less than that. And questions? Okay, guys. So 616. So so that's all I want to cover today. I'll stick around. So just to talk about next week's to do, it's on the site now, but I'd like you to revisit the management sim and add a little more to it and change the structure. So what I'm looking for is, now we've talked a little bit about functions, go back and take what you had, right, and structure it so that it uses functions. It'll be a lot nicer and cleaner. And while you're at it, add some new stuff. So at a minimum, I'm looking for there should be a function to output the current state, which might be involved or might not be, right? Tell the player everything that's going on right now. In my example, it was saying, you've got this much food and this much gold, but And there should be a function that presents the user with their current options, right? Bonus points if you make some of those options not always available, right? So if my gold is 0, I probably shouldn't see the option buy food for gold, right? If my food is 0, I should have the option to sell food for gold. And, add a few new things.